everyone, welcome to the second video of M3 with Sylvia. This is another video in the category of math. If you're wondering where the music and more are, don't worry, those will be coming very soon. So today we're going to talk about geometric series. A series is a sum of all the terms of a sequence, and a sequence is just a sequence of numbers. It doesn't have to be in a common ratio or have a common difference, but geometric series have a common ratio between the terms. So first, let's define a geometric series, or find one of the generalized forms. So this is the generalized form, where A is the starting term, R is a common ratio, and N is the number of terms. Of course, this is the equation for a finite geometric series. So let's look at a few examples. There's 1 plus 2 plus 4 plus 8, 1 plus 3 plus 9 plus 27, and 1 plus 4 plus 16 plus 64, just to name a few. We'll be evaluating probably the middle one in this video, because this is very easy to calculate by hand. And even though this is also, it's a little bit more time consuming, only a little bit, but let's just evaluate it using geometric sequences and series. Let's set that equal to S. So 3S would be 3 plus 9 plus 27 plus 81. Notice that these terms all match up. And now we can subtract S from 3S. So 2S would equal 81 minus 1, because everything except 81 and 1 cancel. So 2S equals 81 and S equals 40. Let's do a calculation by hand check. So 1 plus 9 is 10, 3 plus 27 is 30, 10 plus 30 is 40. So yes, this method does work. You might be wondering if there is a formula for the finite ones, and luckily there is. So let's go back to this form. A plus AR plus AR squared plus all the way to AR to the N minus 1. And let's once again set that equal to S. And R is a common ratio, right? Let's multiply the entire sequence by R. To A, R, and N. And notice how this term and this term and all these terms, they would all match up. So we have R minus 1 times S is equal to AR N minus A. So R minus 1 times S equals A R to the N minus 1. We can divide by R minus 1 to find S. It's the general formula for a finite geometric sequence. And now let's look at infinity. Yay, infinity. People like infinity in terms of money and bliss and all that kind of things. And some mathematicians like infinity in terms of geometric sequences and series, because sometimes they lead to the concept of a limit. And limits, well, they're a calculus topic, but just to get the idea of them, they're pretty cool. So a geometric sequence, well, an infinite geometric sequence or series is very similar, only it doesn't end at a r to the n. This keeps going. And r, the absolute value of r has to be less than 1. Not less than or equal to, strictly less than. Because if r is greater than 1, r squared, r cubed, all those exponents will just keep getting bigger and bigger and bigger. So the terms will just keep getting bigger and bigger and bigger. And since it's an infinite geometric series, it just tends to infinity. And if r is negative, then a is, well, it will be a minus ar. Well, it will be positive, negative, or negative, positive, depending if a is negative or not. But then it just keeps going back and forth from a very big negative number to a very big positive number. And if r is equal to 1, it's just a plus a plus a plus a plus a, all the way on forever. And if it's negative 1, a minus a plus a, it just becomes indeterminate because infinity is neither odd nor even. So then it's impossible to tell if it's a or 0. And now let's take a few visualizations. So let's just take this regular box with side length 1, square. And let's take half of that. That's just half. And half of the remainder. That's half times half, or 1/2 squared. So a would be half, and r would be half. And half of that, and so on. And the unshaded part, it just keeps getting smaller and smaller and smaller and smaller. And if we go on to infinity, which I won't draw because that would take an infinite amount of time, well, you would think that it just gets infinitesimally small. It just tends to 0. And so it seems that it tends to 1. The sum is 1. Not quite clear enough. Let's do 2 more examples. This 1/3 won't be quite so easy to draw. There'll be enough. Visualize it. 1/3 plus 1/3 squared plus 1/3 cubed, and it's going to be really hard to divide that bit there into thirds, and because it would be really, really thin. But it already looks kind of like it would end at 1/2, right? So, one more example. A regular equilateral triangle with side length of 1. And we divide it into 4 equal pieces and shade one of them. Take the remainder, shade that, the remainder shade. And it seems that 1 out of these 3, 1 out of these 3, 1 out of these 3, and 1 out of the tiny 3 that would be up there. And it looks like it would be 1/3, right? But looks like isn't enough. Luckily, there is a formula for this kind of thing. So we have S, that's the infinite geometric series. Over here, we can put that right here. A plus AR plus AR squared plus on and on. And RS equals AR plus AR squared plus on and on. And you might notice that these terms and these terms, and probably on and on, they will all just match up. So when we subtract RS from S, we'll just be left with A. So let's just do that. 1 minus R times S is equal to A. And hey presto, that gives us an easy formula. S equals A over 1 minus R. And this doesn't really look like this one up here, right? Well, n would be infinity in an infinite geometric series, right? So n, r to the n, when r, the absolute value of r is less than 1, it would just tend to 0. So 0 minus 1 equals -1. So negative a over r minus 1 And then we can move the negative from a to the r minus 1. The negative of r minus 1 is 1 minus r, and that gives us our equation right here. That's all for this video. If you have any questions, feel free to post them in the comments, or any unclear math topics, post that too, and I'll try to make a video about them. Thanks, and goodbye!